Il est toujours prêt, hein.
So, hello everybody. Hello all the participants of Al-Khwarizmi Applied Mathematics webinar. It is truly a great pleasure for me to welcome and introduce Professor Jean Bertoin today as a speaker in Al-Khwarizmi Applied Mathematics webinar. This moment is particularly special for me as I have known Jean for almost 30 years, dating back to my time at the University of Paris 6, where he was a professor. Professor Bertoin obtained his doctorate in 1987 from the University of Paris 6 under the supervision of Marquiot, with a thesis in Dirichlet processes. He spent many years teaching and conducting research in Paris and is now a professor at the University of Zurich. His outstanding contributions to probability theory have been widely recognized. He was awarded the Rollo Davidson Prize in 1996, and he has been an invited speaker at major and prestigious mathematical conferences, including the International Congress of Mathematicians in Begins 2002 and the European Congress of Mathematicians in Krakow 2012. He is also a corresponding member of the Mexican Academy of Science. His research covers fundamental topics such as Levy processes, Brownian motion, branching processes, random fragmentation, and coalescence processes. Despite his many commitment, Professor Bertoin kindly accepted our invitation to be one of our speakers today. John, thank you for your trust in this webinar and for taking the time to join us. The floor is yours.
Well, thank you very much, Rafik. It's a great pleasure to be speaking at this webinar, and a great pleasure to see you again and Wissam as well. So I will speak today on quite recent work on population model with memory, as the title says. I cannot...
You cannot change the...
Change the slides, or maybe there.
Try Control L.
Control L.
To be full screen.
Oh,
Yes.
okay, yeah. And then maybe...
With...
Yeah. Okay. So to start with, it's let me say a few words about family, and in particular when a child is born in a family. Something one does quite frequently is to try to single out resemblances with parents. So you can say, for instance, that the child has the same eyes as the mother or as the father. And from time to time, you cannot really assert that the trait comes from one of the two parents, but you have to go further generation away. So, for instance, the nose or the mouth reminds you of the grandparent, and it can even go much further than that. So probably something which is less known is, so it's due to the fact that the genes which whose expression gives the trait of the person, of the individual, can remain dormant in the DNA for many generations. So in the examples I just described, it's for 1, 2, possibly 3 more generations, but it's probably less well known that dormancy can occur for a great many generations. And there are famous examples in the literature, in evolutionary biology. So for instance, some unfortunate children can be born with tails, true tails, which is a rest of very far away history. Even more surprising, you can grow chicken with teeth. So that's a reptilian trait from a chicken. So this trait is dormant in chicken, but it can be reactivated by suppressing some control in the DNA. It means really it goes, yes, probably something like millions of generations backwards in time. And this phenomenon is known as atavism. So here I copied a definition given by Wagner, a famous researcher in this area. So technically, it's a morphophysiological trait, which is controlled by an ancient gene. And this trait can survive for very long periods of disuse. So you do not see this trait expressed during many, many generations. And at some point, it's reactivated and reused in later lineages. And as I said, this how long it can survive in a dormant state is quite, well, very, very important. Okay. So when you have such a phenomenon in evolutionary biology, there is always the question of, in a sense, economy. So it's very expensive for living organism to retain memories. And one can wonder what is the advantage given by atavism. If it prevails, if you can observe it in the current population, so this means that it must have an advantage in terms of selection. And the common view in this setting is that atavism strengthens the adaptability and the survival potential of the population. The idea is a little bit like when you are doing home improvements at home. So you have a large toolbox, and sometimes you have tools or pieces which you will save in your box, knowing that probably you don't have immediate use for it, but you are thinking that maybe later on this might be useful again. And the reason why atavism is favorable in the population is that from time to time you can have modification of the environment, or for some reasons, solutions which were given by evolution and have been forgotten by the condition change. The condition change again, and in your toolbox, in the toolbox of the individual, the solutions which were then found are still available. And this is much quicker than following the path of evolution again. So you have already in your toolbox the solution to the new environment. So for instance, this has been observed in a lizard which were transported from one island to another island, where the ecological situation was much different, and you saw a transformation of their jaws. They were on one island eating soft fruits, and then on the new island they had to had food which was much harder and needed stronger jaw. So long ago in their past, those lizards had strong jaws. The strong jaw disappeared because they were able to eat soft fruits. And at the time, the modification takes place when these lizards were transported. Then again, there was a necessity of building much stronger jaws. And this gene already existed in their toolbox, in their ancestry. And so the adaptation went extremely fast. And that's the reason why it's economically advantageous to have this possibility. What I would like to present in this talk is actually, even without speaking of evolution, even without speaking of selection and of changes of environment, it's always beneficial for population models to use memory from the previous generations for the reproduction. Okay, and to do so, maybe one heuristic explanation first. So imagine that in a population, you have ancestors who are extremely prolific. And if you have kept the genetical material of those ancestors in the current population. So because they were extremely prolific in the sense that they had generated a large descendants, and then a large proportion of the current population will retain genetic material from those prolific ancestors. And if it has the possibility of being activated again, then in turn, it will produce a large descent in the future. So the result, in a sense, is not really surprising, but there are mathematical arguments for this, which are, in my view, interesting. So to do so, we will compare two models. One model without memory, which will be the benchmark model, and the model with memory. Okay. So the benchmark model for our study is a population without memory, and it's given by the classical multi-type branching process. And for the sake of simplicity, I will assume that the state of space of types S is a finite type. So for instance, you can imagine colors of eyes or whatsoever. It can be very large, but it's finite. And in this setting, the dynamics of the process is governed by what we call the basic reproduction kernel. So this is this quantity pi of S and N. So here, S is a type. So it's a type of the parent. And N is an integer vector. So the indices are on the space of types. And N of T is a number of children of type T, which is produced by an individual of type S. Okay, so here, this pi S of N is the probability that an ancestor of type S gives N of T children of type T for each T in the space of type. So I hope that the model is clear. And this basic reproduction kernel completely characterizes the evolution of the process. Then it's a branching process, meaning that given their types, individuals reproduce independently one from the other. Okay. So in this setting, it's well known that the asymptotic behavior of the branching process can be characterized by the spectral properties of the mean reproduction matrix. So the mean reproduction matrix is denoted by M. So it depends on two parameters, S and T, which are types. And the M of S and T, so that the entry at S and T is given by the expectation of the number of children of type T, given that the ancestor has type S. Okay, and you take the sum over all possibilities. Okay, so that's on average how many individuals of type T does an ancestor of type S produce. Okay, so you have this mean reproduction matrix, and and this mean reproduction matrix is a square matrix. The space of types S is finite, and the entries, of course, are non-negative. It's an expectation of number of children which are born. And we will always assume that this mean reproduction matrix is irreducible and aperiodic. So said in a simple way, this means that you can find a power of this matrix, sufficiently large power, so that all the entries are strictly positive. Okay, when you raise this matrix to a sufficiently large power, you get something strictly positive. So in this setting, the important quantity is the spectral radius of your matrix. So I denote it by R. It's the maximal of the modulus of the eigenvalue. Actually, it's a real number. And by a well-known formula due to Gelfand, you can also express it as a limit of the operator norm of the matrix m to the power n. You take this its matrix norm and raise it to the power 1 over n. So this is this sequence is actually non-increasing. It possesses a limit, and this limit is given by the maximal, the spectral radius, the maximal eigenvalue. So then, by the Perron-Frobenius theorem, this spectral radius is actually an eigenvalue of your matrix. It's a simple eigenvalue by the assumption that it is the matrix is irreducible and aperiodic. And you know that there exists, you can choose left eigenvector, rho, which will be a probability measure. So the probability measure rho on the space of types. And here is the equation saying that this probability measure is a left eigenvector of the reproduction matrix corresponding to the eigenvalue R. Okay, so this is a classical theorem of linear algebra. And in this setting, it's known that the growth on average of the multi-type branching process is governed by this leading eigenvalue, this Perron-Frobenius eigenvalue. So m to the power n times the vector 1, this represents the size of the population after n generations, and it grows like r to the n. Okay, so the Perron-Frobenius, or the spectral radius, determines the growth of the population. And what is the role in this setting of the eigenvector rho, the priority vector? It describes asymptotically the repartition of types in your population. So to be more specific, m to the n means that you are looking at the population after n generation. This indicator function of the type S means that you are counting how many individuals with type S you can observe in the population. So you know that essentially you will have of order r to the n of them. So you renormalize it by r to the minus n. And as n tends to infinity, this converges to the coefficient rho of S of your left eigenvector. Okay, so the situation in the case without memory is very classical and well understood for many years. Now, what is the model with memory? So for this, I will use the red color to stress that I'm dealing with the process with memory, because, well, otherwise one would have difficulties to identify the symbols. And now you imagine that every individual not only has a type, but actually keeps track of all the types of all its ancestors. So now the memory of an individual, S in red, is given by a sequence of types. So here, S0 is the type of the individual itself. S1 is the type of its parent. S2 the type of its grandparent, and so on, until as long as you can go back. And Sj, so more generally, Sj is the type of the forebear at generation j backwards in time. Okay, so you call this red S the memory of an individual. And how does reproduction, what are the dynamics of reproduction in this setting? So for each individual, you will pick a generation T at random in the memory. And so you get a type S of T, which is not the type necessarily of your individual. It's a type of one of its ancestors. And you will reproduce according to that type, not according to the type of the individual, but according to the type of the ancestors that you have picked at random. So this means that given that the type that you have chosen is S prime, then you reproduce according to the reproduction kernel pi, but at S prime, not at S0. Okay? Okay, so imagine now that you have a child which is born with type T from a parent which already had memory S red. Then the memory of the child is denoted by TS, and it's simply a concatenation. So you have the type of the child which is born, and then the sequence of the types of its ancestors. Okay? So I hope that the model is clear. Essentially, for each individual, you choose at random, according to a fixed distribution, the type of one of its ancestor, and instead of reproducing as in the memoryless case as the type of the using the reproduction kernel of the type of the individual itself, you use the type of the ancestor. Okay, so we assume furthermore that independent and identically distributed variables T, those which select the ancestor, the generation of the ancestor you use for the reproduction, are activated for different individuals, and you get your this way your model of population model with memory. The only thing which we assume about the random generation which are activated, so these are with a fixed law tau, you assume that the probability that this generation is a zero generation is strictly positive. So you have a strictly positive probability of reproducing according to the type of yourself. And you assume also that you do not go too much backwards in the generation, so that the expectation of T is finite, which is both are very minor condition.
Can I ask a question, Jean,
yeah, sure.
please? So every child has the same probability distribution for their production as the chosen parent.
Absolutely.
Okay?
Yeah.
Okay. But because they must have the same ancestor, the same first ancestor, there are no change of the probability distribution.
No, there is no change of the probability distribution.
So if the population starts by only one element.
Okay.
Okay, the child have to choose the same distribution as the parent.
Yeah.
And the second generation, the same thing. Okay, because
well, it's convenient for the model to assume that you have already observed you are already starting from infinitely many generations. So every individual that you are observing has already an infinite generation backwards. It's not a spontaneous creation of individuals. Every individual has already an infinite history behind itself.
Okay.
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 So it's and that's the reason why you can select a generation with a given distribution for any individual in your population. So just imagine that your population has been existing for, or at least you concentrate on individuals which have an infinite history. I prefer to keep this this setting because it avoids some technicalities. But you are right. You could also consider models in which there is a first born individual, and then in that case the generation T that you pick cannot exceed the number of generation backwards.
Okay.
But that would be a bit different, and this situation is easier to analyze.
Okay. And what does mean capital T equals 0. That means that the child...
Okay, T equals 0 means that you reproduce according to your own type.
Okay, yes.
Okay,
Okay.
you do not need to go backwards in the generation.
Okay.
Really your type, which is activated. And I would say if you pretend that this model has any sense, probably the probability that T equals to 0 is very large, because you are more likely to use the information of yourself than the information given by some remote ancestor.
Okay.
But you can imagine, for instance, that the distribution tau is, well, tau of k is decaying with k.
Mm-hmm.
Okay?
Okay, thank you.
But that's not really needed. All what you need is that with a strictly positive probability, you can choose yourself. And the average number of generation you have to look backwards is finite.
Okay, thank you.
Okay. But possibly tau needs not to be a bounded variable. It can be as large as you wish.
Okay.
Okay.
Okay, thank you.
Okay, so this population model with memory can also be seen as a branching process with types, except that now the space of types is a space of memories, and it's no longer a finite space. So the space of types of individuals is this red S. So it's a space of sequences indexed by non-negative integers and sequences of types. Okay, so it's an uncountable space of types, and you can nonetheless equip it with a natural distance and make it a compact space. So that's, from the point of view of branching processes, it's not that bad if you have a compact space of type. And in that setting, what replaces the notion of a mean reproduction matrix is a mean reproduction operator. So I denote it again. Well, I lost my. I denote it. I don't see my pointer. No. I denote it again by M with a red. So red means that it's something which acts on sequences. And the mean reproduction operator is defined as follows. So it's, I would like to have, okay. So the mean reproduction operator acts on spaces of functions from the space of memory, and the functions are real functions. And MF of S, so this represents the average evaluated according to the function f when you have a parent who has memory S. On average, what will be the repartition of the children it produces? So let's analyze this formula with some details. So S here, the red S, is the memory of the parent. This means that you have a child which has type T, and therefore the memory of the child is obtained by the concatenation of T and the memory of the parent. It's a TS. So you evaluate your test function f at TS. That's the evaluation of the child. Now, what is the probability of getting a child with type T? So this is given by this quantity here, this M of Sj and T. So remember that things in letters in black are for the memoryless process. So here, this is on average, when you have a type Sj which is activated, how many children of type T do you get? So this is this quantity M of Sj and T, and you multiply it by your test function. Take the sum over all the possible types of for the children. And now what is the probability of having chosen Sj? further reproduction. So when you activate the memory, and it's given by this tau of j here. So tau of j is a probability that you go backwards j generation to activate the memory, and then Sj is the type of the ancestor at the jth generation. And you take the sum for all the possible values of j in your memory. Okay, so this is the operator which replaces the mean reproduction matrix in the memoryless setting. And there is a relatively easy lemma because you have an explicit expression for this operator. It's as I said, the space of memory S can be made a compact space. It's a metric compact space, and the Feller property always holds in this setting. So Feller property means that if you apply this operator to a continuous function of the space of memory, then you get again a continuous function of the space of memory. So this is this first assertion. And nonetheless, and this is a bad news for when you are dealing with spaces of types which are uncountable, the strong Feller property fails. So the strong Feller property would mean that if you now apply your operator to a function which is simply Borel measurable and bounded, then you get a continuous function. So that would be the strong Feller property. And unfortunately, it always fails as soon as the support of tau is unbounded. So it's a problem, and I will explain in a while why this is something a bit annoying. So nonetheless, what I explained in the setting of multi-type Galton-Watson processors when the space of type is finite still holds in this setting. So you have an operator, you can compute its spectral radius of M, and I denote it by this red R. And a bit like in the Perron-Frobenius theorem, you can see that this red R is indeed a left eigenvalue of the operator M. So this was obvious in the case when the space of type is finite. This may hold or may not always hold in the case when the space of type is compact or a locally compact space. But much more interestingly, the fact that the spectral radius with memory is always greater than or equal to the spectral radius of the mean reproduction matrix R. And the interpretation is now clear. As we explained a few minutes ago, the spectral radius determines the rate of growth of your population. Okay, so the interpretation of this very simple inequality is that on average, the population with memory grows always at least as fast as the population without memory. Okay, so that's what the motivation I gave for this study at the very beginning. Okay, so how do you analyze it? Well, maybe first of all, I would like to present an example because it's, well, typically you cannot do very explicit calculations. The dimension is very soon too large for this. But let's consider the most elementary case. So you have only two types, A and B. So the space of type S is a set of cardinality 2. And let's say, just for simplicity, that the mean reproduction matrix M is this one, 1, 1, 1, 2. So this means that if you have a parent of type A, then on average, you will have one child of type A and also one child of type B. And on the other hand, if you have a parent of type B, then you have on average one child of type A, and also now two children of type B. Okay. So you can compute, it's a 2x2 matrix, so you can compute the eigenvalues, find the largest of them, and what you get is that the spectral radius of this matrix is 3 plus root 5 divided by 2, so that's about 2.6. Now, introduce the memory. So to introduce the memory, this is governed by the distribution tau, so that's the law of the random variable capital T. And because you're, for the sake of simplicity, I will just take, I also lost my pointer. Okay. I will take a Bernoulli law with parameter U. So this means that the probability that T equals 1 is U. The probability that T is equal to 0 is 1 minus U. Okay. And in that situation, because the memory can have at most length 2, this means that you need not to consider infinite memories. It's sufficient to stop after 2 terms. So the space of memory sequences, actually, you can restrict your attention to memory sequences of length 2 because you never use memory after generation 2. And you have in therefore 4 possible memories which you can have a memory AA, so you are of type A and your parent was also of type A. Memory AB, meaning that you are of type A and your parent was of type B. Here, BA means that you are of type B, the parent was of type A. And BB, both you and your parent were of type B. You can compute the matrix now of the mean reproduction matrix, but with memory, and you get this 4x4 matrix. So calculations are maybe a bit more complicated already, but they are still doable, at least numerically. And this is what you get as a result. So the spectral radius of the process with memory is this, has been drawn here in red. And you see that it's, well, there is a difference. It's indeed larger. So the value 2.618 is here and here. But the spectral radius, depending on the memory, can be a bit larger, something like about 1% of the spectral radius of the process without memory. And this 1% still makes a difference. So this means that essentially after 100 generations, you will have twice as many, on average, population which will be twice larger than for the model without memory. So it takes some time. I was a bit surprised to see that the difference was so small, but that's what this example shows. Okay, so how do you prove things now mathematically? The idea is to use, there are 2 ideas. The first is to analyze the powers of your operator using a so-called many-to-one formula, which is a classical technique in branching processors. And essentially, this enables you to relate the power of a non-Markovian operator, which is this operator in red M that you had, with a Markov operator using a multiplicative functional and a so-called Bayes Markov chain. So I will give this many-to-one formula in a moment. Let me just stress that in general, there is a great variety of formulas that you can obtain. There are a great number of choices for the multiplicative functionals and the Bayes Markov chains that you may obtain. But for us, you can make clever choices, and this will be using the spectral properties of the models without memory. And the second key ingredient is to analyze the behavior of the biased chains, and in particular the ergodic property. And I will explain this in a moment. Okay, so how do you construct this biased chain? Well, it's maybe a bit less intuitive than we might expect. We will not only work with the memory of an individual, but we will also recall. We will also recall the type of the ancestor which has been activated for its procreation, so that we do not only recall the whole memory, but also keep track of the type of the forebear which has been activated at the moment of the reproduction. And so you may recall that the black R is the spectral radius of the mean reproduction matrix, so then in the model without memory. And from the Bertoin theorem, that there exists a unique pair of solution to the eigenproblem. So we spoke about rho, which was the left eigenfunction. I did not yet speak about h, which is a right eigenfunction. But in any case, so you can find such a pair. Rho is a probability measure, h is a function. Both have strictly positive coordinates. The first identity here means that rho is a left eigenvector for the maximal eigenvalue r. And here, similarly, h is the right eigenvector for the same eigenvalue. The normalization, in order to have uniqueness, has been chosen so that rho is a probability measure, and h has non-negative values, and the rho of h is just the sum of rho of s, h of s. It's the integral of h against s has to be equal to. So you choose rho, or you solve your eigenproblem like this. And this allows you to construct, you will modify the mean reproduction matrix and normalize it in the following way. So, so this is the expression in this formula. So on the, I don't see my, you multiply by your mean reproduction matrix with h of t, the right eigenvector, and you divide things by r times h of s, where r is your Perron-Frobenius eigenvalue. So you see, if you take the sum over all t of this quantity, the denominator does not involve t, because h is an eigenvector with for the eigenvalue r, what you get here is exactly the denominator. Okay, so the sum of this quantity for all t will be equal to 1. Equal to 1. So you get a probability measure. Okay. Okay. Next, you are not interested in this black operators, but rather in the red one. And this notation enables you to introduce now a Markovian transition kernel on the space of pairs given by types and memories, which is given by this. So it's essentially it's very close to the formula which I showed you for which I gave you for the non-Markovian operator mred. The only difference is that here the m bar replaces the m there, but otherwise it's exactly the same formula. And the upshot of this transformation is that now this q bar is a Markovian transition kernel. So you have a Markov chain, a Markov process associated to this transition kernel. So what is the many-to-one formula in this setting? So first of all, you construct a Markov chain, which I denote by x bar red, Markov chain in the space of types times memory with this transition kernel. And then the quantity you are interested in, so you take the case power of your operator, M, and it's given by in this form. So you can express it as a functional of your Markov chain X bar. And so this is the expression. So this is the multiplicative formula, the multiplicative functional, sorry, which I announced a few minutes ago. So it's given by a product of h of yy divided by x, yj, sorry, divided by h of xj. So yj is the first coordinate of your process at time j, and the xj in black is the first coordinate of your memory sequence at time j. Okay, so this is once you have taken the right definition, this many-to-one formula is very easy to establish. Essentially, you check it first for k equals 1, and then iteratively you get the general formula. So once again, what is the upshot of this? It's that it enables you to express the case iterate of your operator, MK, in terms of a Markov chain. And there is this multiplicative functional which appears, and you have to understand the behavior of this quantity. Okay. So essentially, this slide is what I just explained. You are interested in the asymptotic behavior of the case power of your operator in red. And it amounts to understanding the asymptotic behavior when k is large of this multiplicative function. And the slight trick here that we will be using is to express this product as the exponential of the logarithm. Okay, so you have exponential of the logarithm, and then this quotient gives you the difference logarithm of h of y minus logarithm of h of xj. So you you may wonder why one expresses things in this way, and the idea is that we can use then the ergodic theorem to analyze both terms. So then you have forget for a moment of the exponential quantity. You have if you divide things by 1 over k, well, you have exactly an ergodic mean of some function of your Markov chain here and there as well. Okay, so the analysis of ergodic property of this biased chain will play an important role in the analysis. Okay, so and this is where you may remember that I stressed that the operator mred was failure but not strong failure, and this is where some difficulty occur, because if you want to, typically when you have a Markov chain on a compact state space, if you wish to establish ergodicity, wish to establish that the process is positive recurrent or something like this, probably the simplest setting to use is that of a Harris chain, or and the fact that the process here is or the operator mred is not strong failure, essentially immediately impedes the application of this of the theory of Harris chain. So it's due to the fact that you retain memory of all your paths, of all the paths that you did precedingly, and as a consequence, if you start from two different memories, then there is no way at some point that you will reach the same states. You can always recover your starting point from your current state. That's the way we constructed our process. So this impedes the use of classical tools in using Harris recurrent change and things like this. But nonetheless, one can show that this kernel Q bar is uniquely ergodic in the sense that there exists a unique stationary distribution, sigma red bar, on the product of types and space, which solves this equation. So it's the equation for being a stationary, an invariant distribution of your Markov chain. And the way you do so, as I said, a typical way of establishing ergodicity in the Harris sense, for instance, is to construct a true coupling. So that means that you will let your process, you have two copies, two versions of your process started from different state space, and you let them evolve and until at some point they reach the same state. And once they have reached the same states, you couple them, the two trajectories coalesce. So here, this is impossible due to the fact that the process has memory. But nonetheless, you can use techniques which were developed by Martin Heirer and Jonathan Mattingly, in a very different setting. And to establish unique ergodicity of your chain, actually, you need not an exact coupling, but it's sufficient to establish the existence of an asymptotic coupling, meaning that even though two chains starting from two different state space will never meet, it's impossible physically, nonetheless, you can couple them in such a way that they will get, after some time, closer and closer one to the other. So they will remain, as time passes, always closer and closer. And this is sufficient to establish the ergodicity, unique ergodicity of your process. Not only can you do that, but you can also compute the marginal of this invariant distribution, sigma red bar. And what you see, so I won't give the details of the calculation, but what you see is that the one-dimensional marginals are all the same. It's not very surprising, but you can check it technically. And in particular, since the one-dimensional marginals are the same, this means that the expectation of logarithm h of y and of logarithm of h of x are the same, and therefore the expectation of the difference is equal to 0. And then it's sufficient to apply the ergodic theorem and Fatou lemma. So using these observations above, you conclude that as k goes to infinity, the limit of the expectation under the stationary distribution of this multiplicative functional is at least equal to 1. And when you go back to the many-to-one formula, this implies this assertion. So you use the many-to-one formula, you get that this limit is always at least 1. It's exponential of 0. And therefore, by Gelfand formula, this shows you that the leading, the spectral radius of your red operator is always at least equal to the spectral radius of your process without memory. Okay, so that's all I wanted to explain. Thank you very much for your attention.
Thank you, Jean, for this nice talk. Are there some questions, please? Some questions? So your R red is bigger than the R black, okay?
Yeah.
And the R red is the radius of what? Okay, the R red is when we have memory. You have full memory, okay? So the R red depends on the distribution of the memory.
Absolutely. Mm-hmm.
Okay. So can I choose some, are there some distributions for tau for that R is very large?
Yeah. That's a very natural and interesting question. And I mean, all I know is just by looking at this example here.
This one, yes.
Yes, it seems on this example that the maximum is reached for u equals half, and u was the parameter of the memory of the Bernoulli.
Yes.
Of
the Bernoulli.
Yes, of the Bernoulli distribution. So I kind of, it's not a conjecture because I'm not sure at all, but it might be that the maximum might be reached for the uniform distribution, as long as you suppose that the support of your memory is bounded. So if it's say you are allowed to go 10 generations backwards, my guess is that maybe the uniform distribution on 0, 10 might be the choice where you reach the maximum. But I try to check that, to prove that, and failed. It seems to be yes, quite difficult to analyze this many-to-one formula and make the analysis of the ergodic properties of this bias chain and get explicit information about this red R.
Okay.
I would say if there is a guess, if I should guess something, I would make that one, so that if you, on the event that you are not allowed to use more than 10 steps of your memory, then the one which will be the best is the uniform memory on 0, 10. In the case when the memory is unbounded, I guess there is no maximum. You cannot get any optimality. But nothing supports this.
Okay.
I have a small question.
Yes, Guy. Yes.
Guy, Jean, I did not understand. I did not see exactly why you were bothered by the non-application of strong failure property.
Okay. Because let me state it this way. What would be a nice way of establishing unique ergodicity of your process? It would be like checking a kind of a Dublin condition, meaning that in your transitions you have, I would say, starting from two different state space, a kind of a common distribution. There is a small chance that you will reach you look at the distribution starting from one state and starting from another state. So these two have a common component, and in that case, you decide that your two trajectories actually will use this common distribution, and then this means that they have reached the same point. I don't know if I'm clear enough, but it's this Dublin type condition.
Yes.
Okay? And this is automatically, this cannot be realized when you do not have this strong failure property. So you see here the because of the memory, even if you are concatenating another type after your sequence, you start with two memory sequences. You can concatenate as many elements as you want. If you start from two different memories, you will never end up with the same state. So your two trajectories, there is no way you can make them end up at the same state, and this ruins the classical coupling methods that you may wish to apply.
Ergodicity, yes, yes. Thank you, thank you. Yes, yes. I see. Thank you.
I think that Dr. Abdul Hakim Babtin has a question.
Yes,
Yeah,
thank you. Yeah, thank you, Professor, for your rich presentation. And it's somewhat, I have some information, new information on it. But my question to you, Professor, is what do you think if you use Bayesian statistics in this case, and this, for example, you use MCMC for generating your data on this analysis?
Unfortunately, I don't know how to answer your question. It's I'm sure it's an interesting way of thinking, but I would not know how to use Bayesian statistics in this setting. So maybe it's just by ignorance, but it's.
For example, how we can estimate the distribution of choosing an ancestor.
To estimate the distribution of tau?
Yes, yes.
Yeah, exactly.
Currently, no idea. I don't know.
Okay, thank you. Yes, Dr. Fathi.
Assalamu alaikum. Salim.
Hello.
Yes, thank you very much for a very nice talk, Jan. In the example where the matrix was 1, 1, 1, 2, 1, 2, I suppose,
yeah.
The radius was about 2.2618.
Absolutely, yeah.
Yes, so it's like 1 plus the golden ratio.
Yeah.
So is this like a coincidence, or is there something more to this fact?
No, I think I just chose this matrix here for the sake of simplicity. So indeed, when you compute the characteristic polynomial, you have a second degree polynomial, you can solve things. But in general, the space of types is as large as you can wish.
Yes.
No, I just chose the simplest non-trivial example, I would say.
It's a prototype. It's probably a fundamental prototype.
Yeah, it's an illustration to show that, well, first, that at least on an example for which you can do explicit calculation, you can verify the statement. Indeed, your curve is above the value R black, which was here.
Yeah.
And what I found striking is that, well, it's a bit above. At most, it's 1% above this statement. So the inequality, well, we might be relatively sharp. So the spectral radius R red is always greater than or equal to the black one. But possibly this inequality, at least on this example, is relatively sharp.
So is it the fact then when you put memory in, is this like more that will help the perseverance of the population, or is it the other way around?
It means that on average, the population with memory grows faster than the population without memory.
So it will help its perseveration. In other words, it will it will have more chance to survive. In other words,
more chance to survive, absolutely. And you can even reach situations where the population without memory will extinct almost surely, meaning that the R black is strictly less than 1. But you can have a red R, which is strictly larger than 1. So you have survival in the case with memory and extinction in the case without memory. And,
right. So in practical terms, cultures that probably try to maybe preserve the genes by intermarriage, etc., then maybe can have more chance to survive than those that diffuse in different directions or have more diversity. You think?
In a sense, yes, because you are the idea. I think that's something I tried to explain at the very beginning.
Yeah, for sure.
This heuristic explanation of the result.
Yes.
If you have a type in your population which is more prolific than the other, in the sense that after a large number of generations, starting from a given type, actually the subpopulation will be larger, then memory allows you to, if you keep memory of your ancestors, then a large part of the current population will have in its memory this beneficial type of the ancestor still present. And so if you activate it again, then in turn, it will increase your population. So that's a rough idea. I think the intuition is relatively simple. But if you want to put this intuition into mathematics, well, it's more demanding. The only way I found was to make this analysis using the many-to-one formula, the analysis of the ergodic property of this bias change, and we finally end up with a result. But it's
so you're trying to answer yes/no type of what the ergodicity type of question, yes. Okay, thank you very much.
Thank you for your
very nice, very clear. Nice to see you and meet you again. Okay. And thank you, John.
Thank you. Dr. Abdel Hakim, have you another question? I think you have another question, Dr. Abdel Hakim Babtin. Okay.
Yes,
yes, please.
Could you repeat?
Yeah, go ahead. Sorry, Dr. Abdel Hakim.
No. Could you repeat what you say, Dr. Rafi?
Okay, I left a reference about a book that I wrote in 1995, 97, and regarding population dynamics that have some similarities with this type of questions that Professor John was speaking about. So maybe it could be a marginal reference. It could be useful in terms of techniques and etc. that we used in that book.
Thank you, Dr. Fatih. Thank you.
Thank you, Dr. Fatih.
I left also my email just in case there is any communication.
Okay, thank you.
Okay, thank you. So, Dr. Abdel Hakim, you have a question?
No, thank you so much. Okay. I just elaborate in why not applying a Bayesian analysis in that.
Yeah. Okay, thank you. Please, if you can go to the plot of Ri for the RU for the example.
Yeah.
Yes. After this slide, yes.
Do you want the graph?
After this slide. Yes. Why this symmetry around 0.5? You have exactly symmetry of RU.
I think it's due to the to the form of the matrix.
Yes. Okay.
Otherwise, I do not expect things to be symmetric. It's really due to
Jean. Last remark. Do you have a paper on this?
Yeah. So this is on archive. I think early January.
Okay. Thank you.
Thank you.
Are there some polyurus types under this model of branching process? I think that are there some this model, is it similar to polyurus types? Some polyurus types? No. This example is exactly a polyurine here.
Not quite, because it would be a polytype, except that you do not choose the balls uniformly at random in your urn.
Yes.
It depends on the time when you introduced the balls. So it would be more like, I would say, a kind of imagine that your urn is a tube.
Mm-hmm.
Pick a ball in the tube, you observe its color, you put it back, and you put another ball at the very beginning of your tube, depending on the color that you observe. So that would be this kind of situation, but it's not an urn in the usual sense.
But your ball that you choose is the grandfather that you choose.
Absolutely. The ball that you choose is the type which you use to activate the reproduction.
Yes.
Yeah. So if you would need to keep track of the generation of the ball in your urn sometimes. If you enrich sufficiently the balls, they do not have only a color, but also keep track of at the time they were introduced. Yes, indeed, you can model it by polyurine urn, but it's I didn't find the setting of polyurns very, very convenient. It's not, you see, polyurns are very closely related to branching processes. There is this observation by Atreya in his thesis, I mean, many years ago, that the two essentially are, well, roughly versions, one of the other. Here, the point is that as soon as you introduce memory, well, you will destroy the branching property because two individuals at the same generation will share a certain common ancestry, and this destroys the branching property. So this means also that in terms of urns, well, it's no longer picking balls uniformly at random. You have to keep track of the time when you introduce that ball in the urn. And this makes the classical analysis more complicated.
Okay. Thank you again, Professor Jean Bertoin, for this nice talk.
Thank you, Rai.
Thank you to all the public. And see you after 2 weeks with Robert Sedgwick.
Okay.
Thank you.
Well, thank you.